Hey, welcome back to our help videos. This is our third help video on 8-20, the 25 objective questions on our test premiere. And we're going to pick up with question number 8. Question number 8 deals with these reactions that are done right here. We are supposed to create an activity series out of these four metals right here: antimony, Sb, chromium, Cr, palladium, Pd, and lead, Pb. This is not the activity series right here. This is just the four metals that we're supposed to put in order based on the results of the four reactions. In reaction number 1, they dropped a piece of chromium into a solution of lead 2 nitrate. How do I know it's lead 2 nitrate? There's a 2 after this. Nitrate is 1 minus, so they crossed a 2 down. So we have lead 2 ions floating around, we have nitrate ions floating around, and we see a reaction occur. What that tells us is chromium right here is more active than the lead that was floating around. Chromium forced lead to take its electrons, and lead precipitated out of solution. What do we know from that? We know that chromium is more active than lead. And right down here, we're tabulating the results. What did we learn from reaction 1 right up here? What did we learn? That chromium is more active than lead. In reaction number 2, they dropped a piece of lead into a solution containing palladium 2 nitrate. A reaction occurred. What do we know? That lead is more active than palladium. Lead forced palladium or palladium to take its electrons. The Pd precipitated from solution. We know that lead is more active than palladium. So in reaction 2, we learn that lead is more active than palladium. In reaction 1, we learn chromium is more active than lead. So we can insert the chromium to the left of lead. So right here is what we've learned from both reaction 1 and 2. In reaction 2, we learned lead is more active than palladium. In reaction 1, we learned that chromium is more active than lead. So we already have 3 out of these 4 metals in order. In reaction 3, antimony is dropped into a solution of reaction 2. Well, what solution did we make in reaction 2? The solution started out with palladium floating around in it, and when the reaction was over, lead replaced the palladium. So the solution now has lead in it. They dropped antimony in it. No reaction occurred. What we learned there in reaction 3 is that lead is more active than antimony. Sb was dropped in, nothing happened, so Sb cannot replace Pb. Pb is more active than antimony. In reaction 1 and 2, we had this order set. So what did we learn? That Sb must be after Pd. Antimony, Sb, must come after Pb. It must come after Pb. Palladium, Pd, is already after Pb. So palladium was already after the Pb. Now the antimony must also be after the Pb. But we don't know which is more active, palladium or antimony. We just learned in reaction 3 that antimony is less active than lead. Antimony, Sb, is less active than lead. And in reaction 2, we learned that palladium is less active than lead. We just don't know who's more active, palladium or antimony. Thank goodness for reaction 4. In reaction 4, palladium is dropped into a solution containing antimony. Antimony, I'm guessing, is 3 plus, because a 3 came down from antimony. Sulfate ions 2 minus, that crisscross came from there. So we have antimony ions floating around. Palladium could not force those out of solution. So what did we learn from that? We learned that antimony is more active than palladium because palladium could not replace the antimony. Why? Antimony is more active. So now we broke this tie. Antimony is more active than lead, or palladium, Pd. So our final order: chromium most, then lead, then antimony, then palladium. That's letter A. Number 9. Which of the reactions is not classified? First one is they're saying is decomposition. In a decomposition, we have one reactant. Yep, we've got one reactant. Falling apart into two or more products. We've got two or more products. That is decomposition. In letter B, we have double displacement. That's where there's an exchange of ions. So the first thing here ends up with the second thing there. So PB and K must trade places if it's double displacement. So K ends up with the nitrate, the lead ends up with the iodide, and for a double displacement reaction, one of three things must happen. We must either produce a gas, no gas. We must produce water, there's no water. Or we must produce a precipitant. There it is. Lead to iodide will not stay in solution. Water cannot keep it pulled apart. It'll precipitate out of solution. Letter B is double displacement. Letter C is combustion. In a combustion reaction, this is the combustion of a hydrocarbon, carbons and hydrogens. Oxygen's is our other reactant. In a combustion, things burn, you need oxygen. And when we're finished, we end up with CO2 and H2O. That's what we ended up with. This is a combustion reaction. How did they balance this thing? That's the one, if you remember, where they use the Hollister rule. We have 14 hydrogens here, so our initial thought is to put a 7 there. But remember, you cannot have an odd number in front of the water, so you double it to 14. 7's doubled to 14. That gives us 28 hydrogens. So we need a 2 in front of here to get 28 hydrogens. The Hollister rule says we do it H, then C, then O, the acronym for Hollister Company. So we did our H's. Now we go to our C's. 12 times 6 is 12, so we need a 12 in front of here. 12 times 1 is 12. And then we finish with our oxygens. We have 2 times 12 is 24, plus 14 times 1 is 14. 24 and 14 is 38, so we need 19 in front. 19 times 2 is 38. Combustion reaction. Letter D, acid-base neutralization reaction. In an acid-base neutralization reaction, we must react an acid with a base. This is sulfuric acid, one of our 6 strongest acids. Here's our hydroxide ion. Here it's with an alkaline earth metal. That is one of our strongest bases. That is the strongest base we can have in solution is the hydroxide ion. What happens in this? Well, the acid-base neutralization reaction is a double displacement in disguise. So what happens here is this. The hydrogen breaks off. The hydrogen ions are floating around. They dissociate from the sulfate ion. The H pluses join up with the OH minuses to make HOH. So the H's come off here and join up with the OH's to make HOH. First thing here joins with the second thing there. The first thing here ends up with the second thing there. So really what happened is the magnesiums exchange places with the hydrogens. Magnesium ends up with the sulfate. There they are. That's an aqueous solution. The hydrogen breaks off. The first thing here joins up with the second thing there. There's our water molecule. We have 2 OHs and we have 2 H pluses, so we would make 2 water molecules. HOH is H2O. We have 1 magnesium here. It'll join with 1 sulfate there. Magnesium's 2 plus, sulfate's 2 minus, crisscross reduce, MgSO4. That is an acid-base neutralization reaction, which is a double displacement in disguise. Double means this one ends up with that one. This one ends up with that one. Synthesis or direct combination. In these kind of reactions, we have one product. 2 or more reactants forming one product. That's the case. This is the synthesis of water. Single displacement reaction. In a single displacement reaction, you have one element bumping another element from solution. So here we go. They're saying this is synthesis, or this is single displacement or replacement. There's our one element. There's our compound. But over on this side, we have a compound in a compound. That is not single. If it was single, the hydrogen would have to be with the oxygen and the carbon would be by itself. The hydrogen could replace the carbon. It didn't happen. It didn't happen. We ended up with the oxygen joining the hydrogen. This is not a single. Single is element, compound makes element, compound. This is compound, element, compound, compound. This is actually a reduction, oxidation reduction called redox. This one does not fit any of our 6 originals. And finally, oxidation reduction. What's happening in here? Well, if we look at this, we have compound, compound, element, compound, compound. I have an element by itself here, and on this side, there's not an element by itself. That's definitely going to be oxidation reduction because we have sulfur here with hydrogens. The sulfur is -2 oxidation number right here. Here it's 0. So sulfur went from -2 up to 0. The sulfur was oxidized. That's what happened. What happened to the iron here? Well, the iron's with chlorides right here. Chloride is 1 minus ionic charge, so the chlorides are -1 oxidation number. We've got 3 of them, so the iron right here must be +3. Over here, it's only with 2 chlorides, so it went to +2. Iron went from +3 down to +2. It was reduced. So the iron was reduced. The sulfur went from -2 up to 0. It was oxidized. When we come back in our next help video, we will take a look at 10, 11, and 12. We'll do the remaining part of this page, 10, 11, and 12, on our next help video. Hopefully the help videos are helping. Thank you.